What's going on, guys? Welcome back. It's good to be here. Hope you're enjoying the videos lately as much as I've been enjoying making them. So, good news to start off the video. My alpha build of CalVPN is complete. Code is ready. It is awesome. I'm just playing with it myself right now. And I am getting ready to sort of put it on the website and tell you guys to go play with it for free. So this is an alpha because we can't promise that everything works perfectly just yet. Don't worry, there's nothing dodgy going on with the software. You're not going to get a virus. I wouldn't do that to you. And if you find any bugs or anything wrong, what you can do is comment on my videos and maybe do a hashtag, CalBug or just CalVPN, because I can search comments on YouTube in my sort of space. So the plan is to roll this out in maybe a few days now, and I will tell you guys, at the start of some video that it's ready and you can go download it. So that is so exciting. I'm so excited. Make sure you sign up for CalVPN if you haven't already. If this is new to you, well, quantum computers are coming, powerful ones that might be able to actually retroactively decrypt all your VPN encrypted data. So a lot of your stuff right now is not safe, and governments could be stealing data all over the place with the intention of breaking it with powerful quantum computers. So you should consider CalVPN. Check it out in the description. Let's get back to the video. I downloaded the video today. I've made a couple system changes, so it should be smoother. Should be no lagging today. So let's see how we go. All right, Kurzgesagt, tell me how it is.
Black holes are the most powerful and extreme things in the universe, and they're wildly weird and complicated. What would happen if you fell inside one, and what are they really? First, we need to talk about space and time. Space and time are the grand stage where the play of the universe unfolds. But space isn't a fixed stage, and time doesn't tick the same for everyone everywhere. In short,
speaking of space-time, in general relativity, I was reading a Quanta magazine article recently, and we've just figured out some new stuff about GR. It's 100 years old, but we're still working a lot of it out. And we've just finally figured out how to deal with these, essentially angular momentum in GR, and how to define it very precisely. But anyway, we'll come back to this, okay? I'll talk about it a little bit later because it's really interesting, but it's a little bit more complicated than what I normally talk about.
Matter bends space, and bent space tells matter how to move. Put some stars and planets on the stage, and it sags underneath them. That misshapen stage, with all its little warps and dips, gives us gravity. Black hole.
It doesn't give us gravity, it is gravity. So the curved space-time itself is what gravity is. So that's a very important distinction.
Do not just bend the stage, they're like trapdoors. Places with so much mass that the universe formed a no-go zone where the rules change. Most black holes form when very massive stars die. We explained this process in detail in our neutron star video. All you need to know now is that in the final moments of really massive stars, their insides implode at nearly a quarter of the speed of light. This packs so much mass so close together, creating something so dense that it sort of breaks the stage of the universe. A black hole with 10 times the mass of the Sun would be barely 60 kilometers across. If you look directly at a black hole, it looks like nothing.
So there's lots we could say and talk about black holes here, but I want to get to, the juice of the video, which is what if you fall into it. So that's why I'm just trying not to say too much here.
Space under their control is blocked by an invisible one-way border called the event horizon. The event horizon forms a shell around a region of space that once entered is shielded from the rest of the universe. Because the black hole trapdoor deforms space so much, not even light can escape it. And with nothing escaping to transfer information from the inside, it's impossible to tell what it really looks like. We can still observe black holes because of their effect on matter. Things can orbit black holes just as they can orbit the Sun or a planet. Many black holes have disks of matter orbiting outside the event horizon. This matter can become incredibly hot, as close orbits can speed this matter up to half the speed of light, and tiny amounts of friction and collisions between particles heat them to 1 billion degrees, making the space
Pretty
around these black holes, ironically, incredibly bright. What would happen if you were to try to
The brightest things in the universe, actually. You might have heard of a quasar before. Well, they're these things we see in the very early universe, and it's basically the accretion disk around supermassive black holes at the centers of, old massive galaxies. It's basically when the black holes are eating so much material from this accretion disk, it glows so bright because as it's like water going into a drain. It increases in speed as it spirals inwards. The matter increases that's falling spiraling into the black hole goes quicker and quicker, and this heats up all of this matter in falling, and then eventually it starts glowing, and then they even shoot off these giant jets at the poles of the black hole. And that you might have even heard of a blazar, which is when those poles are pointed at us. Crazy bright. They can shine way brighter than galaxies, and they're the furthest things we can see.
Close inside a black hole. First of all, you'd see the strangest funhouse mirror in the universe. Black hole, gravity is so strong near them that light can orbit too. If you hovered just outside the event horizon at the photon sphere in any direction, you just see yourself. Straight ahead would be the back of your own head, as light from your back travels around the black hole to your eyes. Gravity also alters the passage of time itself. The stronger the gravity, the slower time passes. While you watch the universe above you speed up, those far away will watch you in slow motion. If you chose to fly away from the black hole...
There's lots we could say here, because obviously this is a rapid video and all these facts, and it's like, why this, why that? You're just going to have to, if you want to go Google it for sure. Because if we explain every single point, we'll be here all day. And it is interesting to know, how can black holes, eat light? Why can't light escape? And, there's lots of things going on there, but we'll just keep watching.
You might find that eons have passed for the rest of the universe, a freakish one-way time travel trip to the future where your loved ones are long dead. But getting close to a black hole can be incredibly dangerous. A painful death by spaghettification awaits you. Because your feet are closer to the black hole than your head, they feel a stronger pull of gravity, enough to pull you apart. As you descend, it gets worse. The pulling gets stronger, your body squeezed thinner and straighter, until you've been reduced to a thin stream of hot plasma, gobbled up in one final slurp, never to be seen again. As you approach the event horizon, a distant observer saw you enter it, seeing you stop and fade. The last light you emit, trickling up and out, away from the event horizon.
Yeah, that is correct.
From your perspective,
from a distant observer, you'd actually never appear to cross the event horizon. You'd get, redder and fainter. But if you had a, good enough instrument, you'd always be able to detect them there. So
the void of the black hole rises up to meet you as light from fewer directions can reach you. The blackness envelops you until your only view of the universe you left is a tiny spot of light.
Okay, that's a decent representation. However, he is missing the fact, let's go back, that
as light from fewer directions,
it would be blue shifted. It would start to change colors. So at this point, before you cross the event horizon, you can actually still get out if you provide enough acceleration away from the event horizon. And so the visuals he showed were really good, except for it should have had the blue shifting of light. So what would happen as you approach that event horizon, the starlight in that dot that he showed would actually begin gravitational blue shifting. And then as you crossed it, the event horizon, it would turn red, the dot, the color of it, red, then white, then blue again, as the microwave background and radio backgrounds turned into the visible spectrum. And that would be your final view of the cosmos, or whatever, like the universe that you were once a part of. But I guess, you're still in the universe. So, and that also assumes that nothing else falls in with you. There's so many counterintuitive things about black holes. For instance, from our perspective, if you were to look at the supermassive black hole at the center of our galaxy, Sagittarius A star, if you were to measure it would appear tiny, right? Like measured in micro arc seconds. But still, if you were to calculate its size in relativity, it'd be kind of a naive figure, because it would still appear 150% larger. And that's pretty much because of the way space-time is curved. So if you were to approach this black hole from about 10 Schwarzschild radii away, well, if you had an object just like it, a geometrical object in uncurved space, it would be about the size of your fist, held at arm's length. However, this black hole, if you approach the same distance, and if you're in like a spaceship, it would like cover the entire front screen. And as you approach the innermost stable circular orbit, which is like 150% of the radius of the event horizon, in front of you will be complete blackness. And then as you cross it, even behind you will become complete blackness again, because of the way these light paths are curved. So for all the physics nerds, this would look a lot like the electric field lines of a point charge if you were to bring it near a conducting sphere. So just as these field lines are bent around the conducting sphere and highly distorted by the charge, the line of sight of these objects, the light, sorry, would be bent like a lot. So all the objects you look at would appear really far behind you, like even the ones in front of you would appear behind you. So if you thought you understood black holes and like they're not too complicated, let me tell you a few things. So the reason why as you approach one, it starts to appear a lot larger than it actually is, like in size and scale, it has to do with the fact that the fabric of the universe is always in motion, right? And once you're inside, space itself is actually moving faster than light. This is why you can't get out. And it's also why you see multiple images of the same object. And you can kind of begin to understand this by asking, like, where the hell is the singularity? So when you fall in, the singularity is in all directions. So, thus, surprisingly, the singularity appears in all directions as well. Wrap your head around that, like it literally appears. So like if you're falling in head first, you know, it'll appear in front of you, but it'll also appear down there as well, below you. This stuff might sound like really counterintuitive, but it's actually not so bad to calculate. And this is actually all for like the simple case of a non-rotating black hole.
Develops you until your only view of the universe you left is a tiny spot of light. Here, inside the event horizon, space and time are so horribly broken that real time travel is possible. So it's probably a good thing that nothing
we're always time traveling, right? We're always traveling into the future.
Gets out. If anything could have...
I wonder if there are ways to get out, you know? I'm sure there are, you know? You might have heard of those warp bubbles and Albuquerque drives and things like that. You know, maybe there is a way to get outside of this, you know, space-time fabric stuff and, you know, possibly escape a black hole.
Could create all sorts of time travel paradoxes and issues that break the universe. As scary as the event horizon is...
I mean, the universe exists, right? So I'm sure it's possible to break it. So many people think, I don't know, there's so many absolutists in physics who think, you know, physics is all there is. And I mean, physics is all there is because it means everything. But I just mean that what we currently understand is probably very insufficient to really know what's going on. Like, I'm sure there's ways of breaking the universe. But after all, it's here and it exists and there's something going on.
Keeps us safe from that drama. Whether you have survived this long doesn't really matter, as now there's only the certainty of crushing death in your near future. Inside the event horizon, space-time itself is so bent and warped that whatever direction you move here, every forward you go leads only towards the center of the black hole.
Yeah, he said that a little confusingly when he said every forward. An easier way to understand it is like every direction is actually pointing towards the singularity, even behind you. Wrap your head around that. Because space is so curved, it all gets curved towards this point of infinite density. Anyway.
Trying to go in any direction only brings you to the center faster. To survive the longest...
Another quirk of it is that, you know, obviously space and time are completely interwoven. So it's like at the singularity is actually your future. So, you know how like, I don't know, what day is it? You know, Tuesday. Well, how Friday is in my future. I can't escape the fact that Friday's coming, at least with my current tech. Like Friday is inevitable for me, unless I die as well, I guess. If you're in a black hole, going to that singularity is as inevitable as Friday is for me right now. That's what it means when you're in that region, because space and time, in there, they're linked.
You must do nothing. In the center of the black hole, we find the singularity.
So if you were to fall into a realistic black hole, a spitting black hole, it would actually be different to what he showed. So for the observer outside, you'd see, instead of just getting fainter and fainter, like onto a non-rotating black hole, it would get whipped around. So a similar thing would happen, but it would get stretched, the image all around the black hole, and get fainter and fainter. And so if you're the one falling in, again, it would be different. You would be, whipped around the black hole very fast, and it would be very different as you went inside towards the singularity, and different parts of your body would touch, the ring at different. So basically, you wouldn't be able to see some parts of your own body as you approach the singularity. A fun little fact: if you were to cross the event horizon of our supermassive black hole, the center of our galaxy, even when the diameter of the event horizon is like 1 light hour, it would only take you like 20 seconds to get to the singularity. It's pretty nuts. So after you cross the event horizon, you wouldn't actually see the singularity because of how weird curved space-time is, and because there's light that would be falling in before you, whilst you fall in, and after you. So this part leads in, like if there was a big enough black hole, like in Interstellar, where you could cross the event horizon without being crushed to bits, well, then there's the possibility of, being funneled into a white hole. And you might have heard of a white hole before. It's kind of like the opposite of a black hole. If black holes are, everything's going towards a singularity. In a white hole, everything is moving away from it, right? Obviously, these things are completely theoretical, but who knows? The universe itself, we could be, from a white hole and inside a black hole. So, yeah, black holes really might lead to other universes. And think about how weird this is, right? So, you've got black holes all over the place. Let's just take the supermassive black holes at the center of galaxies. And, at the center of these galaxies, it takes you essentially to another place, another universe, because it's got infinite curvature at the singularity. So now think about this. If there's a whole universe in there, which has its own galaxies and black holes, you go into those, and it's never ending. It's like this infinite cycle all the way down. Kind of mind-blowing. And unfortunately, all of this, white hole, another universe, another reality, all hidden behind the event horizons of black holes. And unfortunately, we just can't see past it. So it's such a crazy thing to think about, because, if you cross the event horizon, even if you accelerated away from the event horizon, the singularity, with infinite acceleration, you're still going to get sucked into it. It's crazy.
A single point with all the matter that has ever crossed the event horizon, all crushed to a point infinitely small. There is no memory of the thing.
Makes a lot of sense, right?
That made it, as stuff disappears down the black hole trapdoor forever.
When he says forever, that's an interesting point. We won't talk about the black hole information paradox. We briefly mentioned it in the last one, but I saw there is a video he does on the information paradox. So we'll go check that out. And I'll just briefly hint, is this information that's going in the black holes lost forever? Well, potentially not. This is an open-ended question currently. So we'll talk more about that in the information paradox video, and, whether black holes are eating dark matter, what dark matter, like how is dark matter involved and related to black holes. We'll talk about that in that next video. So make sure you come back.
Makes all things equal. This actually breaks the universe in really cool ways. We've made a video about this problem if you want to learn more.
Oh, there you go.
But in a nutshell, everything
We'll
that
be
comes
watching
too
that one.
close becomes black hole matter concentrated at the singularity. This lack of a memory of its part, black hole has only 3 properties: its mass, spin, and electric charge. Everything else is lost. They're a lot like fundamental particles in that respect. This actually means that every single black hole in the universe is the same. Sure, their mass is different and some spin faster than others, but if we were to put all the singularities into a magical physics museum, they'd be identical, like electrons. But just like fundamental particles, the properties of singularities are the best ways we can describe them on paper, rather than an accurate representation of reality. Our current theories about the universe, namely general relativity, are just not able to describe or explain them. The curvature of space becomes infinite, density becomes infinite, and our rules just don't make sense. The singularity has no surface or size, something like a divide by zero error in the universe. So singularities might not even exist, or be completely different things. But this is all we know right now from the best prediction we have from our best current theory of space-time.
That's perfect. He's done a brilliant job.
Also, basically everything you've ever heard about black holes, even in this video, is about theoretical black holes that aren't spinning because their maths is so much easier. But since black holes were born from dying stars that were spinning extremely quickly in their final moments, as far as we know, all black holes in the universe should be spinning right now. At incredible...
This is because of the conservation of angular momentum, and like I said earlier in the video, we just figured some more stuff out in GR, and you might know that black hole math has everything to do with GR. So it's an important thing, and there's lots of important results coming out recently about, like as he just mentioned, spinning black holes and how complicated the math is. Well, this results in us not really being able to explain, like, I mean, we can explain, but precisely with mathematical detail, mergers of black holes. It's still, you know, pretty tough, and there's lots of interesting science going on. We still don't completely understand. I thought I'd just throw that in there. There's always things, you know, we're working on that we don't understand.
Speeds too, up to 90% of the speed of light. This means that in reality, black holes...
Maybe we'll talk about naked singularities as well in a minute, because they are really exciting. Like, and we've wondered if naked singularities actually exist in nature, you know, without the event horizon.
Are even more screwed up than they usually get credit for. The singularities of rotating black holes are even wilder. The rotation causes them to swell outwards into a sort of ringularity.
It's also a one-dimensional ring, and the radius of that ring is actually determined by the mass and angular momentum of the black hole. And there's actually a maximum angular momentum to mass ratio that's kind of like allowed. And if there's too much angular momentum, I'm talking about spin here, by the way, like black hole spinning, the black hole actually radiated away via gravitational radiation until, you know, it's at an acceptable angular momentum.
This rotation is so powerful that space itself is dragged along. This creates another region around spinning black holes called the ergosphere, where it's impossible to stay still no matter how hard you try.
If you want to look more into this, our last video we talked all about it and how spaceships might be able to use these regions to, you know, get around the universe, and even how you can make a black hole bomb and take energy from black holes using this region. So you should go check out that last video.
Like a rushing whirlpool of space-time, the tide is irresistible, and the black hole makes you orbit it whether you want to or not. Okay, so what will happen to black holes as...
So he hasn't mentioned this in this video, but just to make it all more complicated for you, realistic black holes, Kerr black holes, rotating black holes with angular momentum, actually have two event horizons, an inner and an outer event horizon. And just outside the outer event horizon is the ergosphere, and that's where this frame dragging occurs, where space itself is getting dragged around at the speed of light.
The universe ages and dies around them. Again, we don't know, but we have some ideas based on our current understanding of physics. Hawking radiation. In quantum field theory, the vacuum of space is boiling with quantum fluctuations. These fluctuations are creating matter and antimatter pairs of particles from nothing, which only exist for a very...
So that's actually a simplification of what's going on. You know, I've said it before as well, and this is how Hawking liked to explain Hawking radiation, but it is a simplification of what's really going on, and it's It's not what's really going on. You don't have particles popping in and out of existence. Unfortunately, it's not. That's not what's going on. It's unfortunately way more complicated and very hard to explain, which is why people resort to this. Because, you know, in quantum field theory, what are the fields? There's really nothing that's analogous. And I'm not going to try and do it here either. So let's just keep watching.
Before annihilating.
You want to go understand, you really got to just jump into the deep end of quantum field theory, because I really do think words, English, fail us here, and because we don't really understand it. You know, quantum field theory is very much an open-ended area. You know, we don't know how gravity fits in with quantum field theory. That's why you've probably heard so much like GR and quantum mechanics don't fit. That's essentially what they're talking about. Quantum field theory, you know, it's the standard model, which is, you know, what you may hear particle physicists talking about all the time, is a quantum field theory. And it encompasses 3 of the fundamental forces, but it doesn't include gravity. We have no idea how gravity fits in.
When this happens near the event horizon of a black hole, one of these particles can fall in, stopping them from annihilating. The escaping particle is Hawking radiation.
Again, so that explanation is how Hawking used to explain it, but it's actually not correct. So,
Black hole, one of these particles can fall in, stopping them from annihilating. The escaping particle is Hawking radiation. Ultimately, the mass of this particle must come from the black hole, so over eons, black holes will shrink and radiate away. Hawking radiation is not the stuff that fell into the black hole, it's new stuff, stealing mass from it. As the black hole shrinks, the Hawking radiation gets stronger, faster and faster.
See, what he just said there might actually be not true because of this information paradox.
Until what's left eventually evaporates in a flash of high-energy radiation like a nuclear bomb. And then, nothing. But that won't happen for a long, long time. A black hole with the mass of our Sun has a lifetime of 10 to the power of 67 years, which means that it would take 10,000 billion years to lose 0.0000001% of its mass.
And that's all according, you know, that depends on if our understanding of things is correct, which we know it's really not complete. We're still missing so much.
But most black holes are
obviously
way
don't trust that.
more massive than our Sun. The most massive supermassive black holes in the centers of galaxies have lifetimes of 10 to the power of 100 years. How long is that? Imagine an hourglass filled with 1 grain of sand for every single particle in the universe. Every 10 billion years, 1 single grain of sand falls to the bottom. If we waited for all the sand to fall down, not even 1% of the lifetimes of these black holes would have passed.
That's
There is no
insane.
good concept to help our brains grasp these timescales.
No.
Will we ever truly understand black holes? Really know what's going on inside them? No one knows.
Oh.
We can only see their outsides, and the theories we have probably get their insides wrong. But it's okay to not know
I love
everything.
that.
It just means there's still work to be done.
Yes.
It means there are still mysteries to solve and big ideas to think about, which is why humans do science. In the end, we can at least be sure that we still have plenty of time left to think about them before the last one melts away.
That was beautiful. What another great video by Kurzgesagt. I loved that. Hope you guys enjoyed. I'll catch you next time.